Chapter 8, Thunderstorms, Mid-Latitude Cyclones and Hurricanes. Section 8.2, Thunderstorms. So we've seen some pictures of thunderstorms. They're the smallest storms that occur on our planet. Range from a couple kilometers in diameter to as much as 100 kilometers in diameter when you have a supercell thunderstorm. Thunderstorms develop when moist, unstable air is lifted vertically into the atmosphere. In fact, thunderstorms can reach a maximum height of 10 to 14 kilometers above the Earth's surface, and they start their development a few kilometers from the Earth's surface. What causes them to lift and form vertically is the release of latent heat energy when water moves from vapor to liquid. This releases a lot of heat energy, and this heat energy acts almost as a hot air balloon in the developing storm. Thunderstorms begin as cumulus clouds, those cauliflower clouds that you often see in the summer months. As soon as lifting begins, this parcel of air begins to cool because of adiabatic expansion. If that cooling results in the release of latent heat energy, the storm will gain energy as it develops with altitude. And this energy addition can be explained by the adiabatic process. Now, adiabatic process refers to the change in temperature with a parcel of air as it moves up or down in the atmosphere. If the parcel is dry and is not releasing any latent heat energy because of the condensation of water, however, with the expansion of air as it moves upward in the atmosphere, temperature cools. The rate of cooling is 10 degrees per 1,000 meters. So here in the diagram on the left, we can see we begin with a parcel of air at 30 degrees Celsius. If it starts increasing in altitude at 1,000 meters, it'll have a temperature of 20 degrees, 2,000 meters, 10 degrees, 3,000 meters, 0 degrees, and at 4,000 meters, the temperature inside the parcel air will be minus 10 degrees Celsius. And this is the adiabatic process. So rising air expands the volume in the parcel and causes it to cool. Now, if we take this parcel and move it back towards the Earth's surface, it will contract, and that will release heat energy, and it will gain temperature at a rate of 10 degrees Celsius per 1,000 meters. On the right, we see the wet adiabatic process. In this diagram, up to 2,000 meters, the temperature change in the parcel of air is a function of the dry adiabatic lapse rate. And this is a rate of 10 degrees Celsius per 1,000 meters. At 2,000 meters, it begins to reach a temperature where the water in the cloud begins to condense. That condensation process releases heat energy into the cloud. And in this diagram, we are seeing about 5 degrees Celsius of heat energy being released for every 1,000 meters. So from 2,000 to 4,000 meters, the rate of temperature change is only 5 degrees Celsius per 1,000 meters, which is the wet adiabatic lapse rate. Now that's quite different than the dry adiabatic lapse rate. If we compare these two diagrams, that cloud on the right at 4,000 meters will have a temperature of 10 degrees Celsius, that parcel of air. If the surrounding air is decreasing at the dry adiabatic lapse rate, the difference between the cloud and the environment, the air around the cloud, will be about 10 degrees Celsius. It will be -10 in the environment. And that temperature difference causes the cloud to act as almost like a hot air balloon, and it will continue to rise, and it will continue to develop until it hits the top of the troposphere, where the inversion layer there stops its vertical ascent. So what happens when a cumulus cloud starts forming? You can see they usually have a flat base. Above that base, the cloud is condensing water. At the base, the cloud has reached its dew point and 100% relative humidity. For a cumulus cloud to form into a thunderstorm, you must have continued uplift. And the amount of uplift is going to be a function of how unstable the atmosphere is relative to the cloud. So unstable means how much colder is it than the developing cloud, the environment, because that's going to influence how quickly it develops in the vertical. Vertical expansion in an unstable atmosphere can continue to cause the cumulus cloud to grow, and at some stage it goes from being a cumulus cloud to a cumulonimbus cloud. Some cumulonimbus clouds near the tropics can reach heights of 20 kilometers above the Earth's surface, but a height of anywhere from 10 to 14 kilometers is more common. So why are thunderstorms considered storms? Because they have often severe weather associated with them. And this severe weather can be in the form of hail, strong winds, thunder, lightning, intense rain, and tornadoes. So here we can see some of the negative effect of thunderstorms in terms of severe weather. We have hailstones, a picture of a hailstone on the top left-hand corner, and on the bottom left-hand corner we can see hail covering the surface of the ground, probably causing some pretty big dents in those cars on them. Another important hazard associated with thunderstorms is lightning, and we can see some images there on the right of lightning. So thunderstorms are usually associated with an unstable air mass. When they form, they don't tend to form alone, they form in clusters. And thunderstorms are often formed in association with mid-latitude cyclones or hurricanes. In a mid-latitude cyclone, they'll form most commonly along the cold front. Hurricanes, those swirling arms of clouds, contain hundreds of thunderstorms going off during the life of that hurricane for that particular day. Thunderstorms are very, very common on our planet. About 40,000 thunderstorms occur on the Earth each day. Most of them are occurring in the tropics. And along the intertropical convergence zone, for any location, there's probably about 100 storms per year, so one every 3 days. They occur seasonally outside the tropics, in the middle latitudes and lower high latitudes when summer arrives over land masses. In the United States, thunderstorm season begins around March and ends in about October. The following map shows the distribution of thunderstorms in the United States. So they're most common in Florida and that southeastern corner of the United States. They're not very common on the northeast coast, and they're also not common in areas of high elevation, so much of the west coast. Notice there's Alaska there. Alaska has very few thunderstorms, basically because it has a short summer, and you need warm, moist air, and it doesn't get warm, moist air for any length of time during the year. I don't have a good map of thunderstorm distribution to show you, but one way that we can sort of use a proxy measure to determine where thunderstorms occur is looking at where lightning strikes occur. So lightning strikes are monitored on our planet from, I think it's satellites, but I think surface measurements too. And here we can see a distribution map of lightning strikes. And I think this is over a 1-year period. So it shows the frequency of lightning events, and you can conclude that those lightning events are being caused by thunderstorms. So the maximum number of thunderstorms seems to be along the equator, especially over land. Africa is a real hot spot. Parts of Central America, Indonesia, and there's also large numbers of thunderstorms over the northern South America, southeastern United States, most of Mexico, parts of Europe. India is a hot spot, and the Southeast Asia is a hot spot for thunderstorm activity. And then thunderstorms are quite common over northern Australia. Notice thunderstorms aren't that common over the oceans, especially where we either have cold water or the presence of the subtropical high pressure systems. Now, the most common type of thunderstorm is called an air mass thunderstorm. We're going to talk about two types of thunderstorms. There's air mass thunderstorms that are pretty mild, and then the more severe called severe thunderstorms. So they are the most common. Heavy rain, a bit of lightning, and are the common effects. Rarely do they have hail or strong winds. These air mass thunderstorms usually develop in the afternoon hours, late afternoon, and their development is a function of surface heating that produces convection currents, and within these currents we have warm bubbles of air that have moisture in them, and they increase in altitude, and at a certain level they reach their dew point and form a cumulus cloud. With continued development, they'll develop into, from a cumulus stage into a thunderstorm. And this diagram shows a simple model of how thunderstorms develop. So there is the cumulus stage, which involves the upward movement of a parcel of air in the atmosphere, clouds developing in that parcel due to condensation. The air currents are upward, like a hot air balloon. When it reaches the top of the tropopause, we've reached the mature stage. The storm stops developing. The winds begin curling back on the back and move towards the Earth's surface. At this stage, rain develops in a portion of the storm with descending winds. These winds are, in a relative sense, pretty strong. And then the last stage is the dissipating stage, and essentially, as the rain falls out, the moisture is gone. The clouds, are no longer developing. They're precipitating out, and the cloud starts dissipating from the ground level upward. until it's completely gone. So what I just described there were the three stages. So once again, the first stage of air mass thunderstorm development is called the cumulus stage. In this stage, parcels of warm, humid air rise and cool to form clusters of puffy white cumulus clouds, which are quite common in the summer months. These clouds develop because of condensation and deposition, so some of it is turning into ice crystals and even snowflakes, and this releases large quantities of latent heat. And this latent heat keeps the air warm, then the air in the cloud, then the environment around the cloud, and makes it buoyant and act like a hot air balloon moving upward into the atmosphere. So there we have the cumulus stage on the left. Here's a picture of some cumulus clouds developing in the vertical over Kelowna. So we can see they're more than just simple cumulus clouds. They do have some vertical development to them. They need to develop a little bit more in the vertical in order to be classified as a cumulonimbus cloud or a thunderstorm cloud. When the updrafts in the cloud reach their maximum altitude, anywhere from 12 to 14 kilometers, the direction of the winds inside the cloud reverse. They change direction by about 180 degrees, and now we don't have updrafts, we have downdrafts occurring in the storm. And this marks the mature stage. These downdrafts move small particles of water. The water droplets collide into each other and coalesce and form bigger droplets until the droplets are large enough to fall out of the cloud. And anyone who's experienced a thunderstorm knows that the raindrops that are falling from these clouds are quite large, and they're moving at a pretty good velocity towards the ground surface. So this is the most intense stage of the cumulonimbus cloud thunderstorm development. This is the stage where you're going to get heavy rains, maybe some strong downdraft winds, and maybe some lightning associated with it in these air mass thunderstorms. So the final stage is the dissipating stage. We'll talk about that in a minute. Here is a picture of a well-developed thunderstorm that I took over Kelowna from Dilworth Mountain. So it's got the classic anvil shape to it. It's reached the top of the troposphere, so it stopped developing. And you can see rain falling from the bottom of it. And you can see that the bottom is flat. So that's the point at which the air reached the dew point temperature and the clouds started developing. These mature thunderstorms, air mass thunderstorms, can have heavy rain, thunder, lightning, and wind gusts, but they don't necessarily have hail or tornadoes. For that to occur, you need these thunderstorms to be enhanced. Something has to enhance the development to make them stronger. When the upward air currents, updrafts, are finished and the downdrafts move all the moisture out of the cloud, we get the dissipating stage, and this stage lasts for an hour or so. The total lifespan of one of these storms is anywhere from 1 to 3 hours. It's not long. Now this is very different from severe thunderstorms, which can last for many hours. They can begin their development in the afternoon and not finish their development till late in the evening. So let's describe these severe thunderstorms. So severe thunderstorms are defined as these convective storms. They have frequent lightning, wind gusts of 97 kilometers per hour, or hail that is 2 centimeters in diameter or larger. And severe thunderstorms can also have tornadoes. Now, the way that severe thunderstorms develop is something moves them along in a west to east direction, and they keep renewing their supply of warm, humid air. In an air mass thunderstorm, the warm, humid air is located beneath the storm, and it rises, and it's not really replaced with new, warm, humid air that could enter the storm. But in a severe thunderstorm, something is moving them along in an easterly direction, allowing them to gain more humid air to continue the development of the storm, the inside of the storm. And this continued supply of heat energy causes a balance between the updrafts and the downdrafts. So the updrafts will occur in the front end of the storm, and downdrafts in the bottom, where you expect to find the rain and the hail. So what's required to push them along? Well, either a cold front or something called a dry line. And a dry line is an area in front of a mid-latitude cyclone cold front where you have a dry sector of air. So you've got the cold front, and then to the right of it, a sector of dry air, and then that ends with the dry line, and then an area of moist air. And these dry lines can be anywhere from 100 to 300 kilometers ahead of the cold front. So severe thunderstorms have particular distribution. They need to be in areas where the mid-latitude cyclone can gain humid, moist air, and that's usually from an ocean body, like the Gulf of Mexico. So in the United States, the primary place where severe thunderstorms occur is central United States, from Texas all the way up to North Dakota and Minnesota. Notice very few severe thunderstorms in Florida. Yet our previous diagram showed us that there was a lot of thunderstorms in Florida. The thunderstorms that occur in Florida are mainly of the air mass type, less of the severe thunderstorm type. So the next two figures display some of the features associated with a severe thunderstorm, sort of a cross-section will be the first one. And as I said, these storms move from left to right, and it's associated, or west to east, and it's associated with mid-latitude cyclone cold front, or this dry line. The storms usually have associated with them an upper level dry wind that's coming in from the west. And in their front, you can see where the warm, moist air is coming in, because they'll have a dark cloud that rolls around, a rolling cloud in the front, just at the base of the storm. So here we can see the features associated with it. Another common feature with severe thunderstorms is mammatus clouds. So you might have seen them. You look up and they look like pillows, little individual pillows. And what you're looking at is the anvil extension coming from the cloud, moving towards the east. Severe thunderstorms also tend to have they have a level top surface, but in the middle they'll have like a bulge, and that's the overshooting top. And so that's where the wind gusts are the strongest, and pushing into the tropopause from below. So in this storm, we can see the balance that exists between the warm air coming in and then the air within the storm, full of moisture, both liquid and solid in the form of hail, moving down to the base of the storm. And the back end of the storms tend to have heavy rain. Hail is in front of it. That descending moist air produces what's known as a gust front. So if you've ever experienced a severe thunderstorm, the passage of it, before the hail and heavy rain comes, Suddenly, you'll go from very still air to air that is rushing past you at 60, 70, 80, 100 kilometers per hour. That's the gust front, the air behind it. And the air suddenly turns cold when that occurs. So you go from warm to cold. Here is another diagram showing some of the features. So there's the anvil, cumulonimbus cloud. So we can see how it's spread out in the top. A whole bunch of smaller clouds underneath it developing. There's a tornado shown in this diagram, the overshooting top, and so on. So just to repeat, so we have both updrafts and downdrafts in one of these mature severe thunderstorms. The updrafts are being supplied with new moist air as the storm is moving from east to west. The downdrafts produce a front at the near the Earth's surface in front of the storm, and as soon as that front passes, it suddenly becomes windy. Winds can exceed 100 kilometers per hour, and they feel very, very cold, and surface pressure increases. Above the gust front is usually a roll cloud, and that roll cloud is being created by warm air flowing past and mixing with some of the cold air from the downdrafts, producing a rolling motion in the front. Some severe thunderstorms, if you look at them with radar, you can see that they actually have a mini cyclone inside them. And these are called mesocyclones, and these can measure anywhere from 3 to 10 kilometers across. And so what that consists of is air that is spinning counterclockwise and upward inside the storm. Mesocyclones are what spawn tornadoes. So these mesocyclones are found in the south west quadrant of the storm. In some cases, mesocyclones can overshoot the top of the storm and form a cloud dome. Sometimes they can shoot out hail from the top of the thunderstorm. About half, if you see a mesocyclone, about half of them create tornadoes that move from the cloud base to the Earth's surface. So here we see the southwest corner of a thunderstorm, and what that swirling coil is, that's the mesocyclone, and then beneath it we can see a tornado developing. And notice tornadoes aren't associated with the rain in the storm. They're in an area where it's updrafts, so you there's no descending air occurring. There's nothing to create hail or rain. So let's talk more about tornadoes, thunderstorms and tornadoes. What the heck is a tornado? And so a tornado is simply a vortex of rapidly moving air that we find associated with some severe thunderstorms. They begin from a mesocyclone within the storm, and they develop by extending from the base of the storm to the Earth's surface. Tornadoes, if they occur over lakes or oceans, they're called waterspouts. And it's not cloud that you're seeing and dust and dirt in the funnel, but actual water. Winds inside a tornado funnel are very, very fast in very severe thunderstorms. They can reach speeds above 450 kilometers per hour. Tornado strength is measured relative to a scale, and it's called the Fujita Tornado Intensity Scale. So not all tornadoes are the same. Some are way more powerful than others. And this scale goes from F0 to an inconceivable F6 that has, an F6 that has winds anywhere from 520 to 610 kilometers per hour. These F6s, none of them have ever been measured, but they're just theoretical. The most powerful tornadoes tend to be the F5s, but still an F5 can have wind speeds from 420 to 313 kilometers per hour. So winds of that speed can throw cars some distance, 100 meters easily. They easily disintegrate homes, even if they're well constructed. They rip bark off trees, and so on. And they're not very common. So F0, the most common, F1, and what we have is a scale, or the number of hurricanes in each one of these decreases exponentially, or increases. If you go from F5 to F0, you're increasing exponentially the number of storms that fall in that category. So here are some images of tornadoes. So what we're seeing here is the condensation of air and the storm carrying up particles of dirt and dust. And it's extending upward to the thunderstorm base, where we have a mesocyclone occurring. When you see pictures of tornadoes, one of the things that's most common, or one thing you notice, is that they don't all look the same, right? Some are narrow, some are wide shaped. In this picture, we can see that cloud in front. That's probably a roll cloud. And you can see that whole area behind the roll cloud would be the mesocyclone, creating this small little tornado at the base that extends to the Earth's surface. And this one's moving towards the surface, and so on. So how long is the typical destructive path of a tornado? Anywhere from about 25 kilometers long, usually no longer than 25 kilometers. And the destructive path is about 500 meters wide on average. Tornadoes don't occur everywhere where there's thunderstorms. In fact, tornadoes are pretty much rare at the tropics, where we have most of our thunderstorms, because most of the thunderstorms there are just air mass thunderstorms. We need this extra lift mechanism to produce a severe thunderstorm that can spawn a tornado. So we need the presence of the mid-latitude cyclone. So some hot spots for tornado formation include South Africa, Australia, Europe, New Zealand, northern India, Canada, Argentina, Uruguay, and the excited states of America. So here we can see days per year with favorable conditions for tornadoes. And there are the locations that I just described. In the excited states of America, tornadoes are most common down the center of the United States, and Florida produces quite a few tornadoes, but they're actually being generated from less severe thunderstorms than what occurs down the center of the United States. Here is a mapping of tornadoes and their strength on that scale, the F scale. So blue dots, dark blue dots represent the F scale, or F0. F1 is light blue. Green is F2, and you can see the F3s, 4s, and 5s have that particular distribution. Thunderstorms don't develop in all months. So here we see for the United States that the most common month of their formation is June. They begin forming in March, but June is the peak. And then there's a secondary peak in October. And those thunderstorms are tornadoes that tend to be associated with hurricane activity. Tornado frequency by hour. So you can see that they really pick up after about 2 o'clock and reach the maximum number of tornadoes by hour is between 6 o'clock and 8 o'clock at night. So this next graph is kind of interesting. Is global warming having any effect on the number of tornadoes that occur in the United States? The trend there looks like yes, but many scientists think no. What we're seeing is maybe there's more thunderstorms due to more intense more tornadoes due to more intense thunderstorms, but it's more likely what we're seeing is better ability to monitor their formation using things like radar. So that, there is an upward trend. Whether that upward trend is because of better detection of them, or is it global warming, is quite a debate going on in the scientific community about that. So tornadoes can cause a large number of human casualties. It's not that common now because of the techniques that we have available. This using radar to detect whether or not they're going to form. We can see that mesocyclone in a thunderstorm before it arrives, and an alarm can sound, and people, hide in protected areas. Before radar existed, there was some tornadoes that took a lot of lives, and the record is held for a tornado that occurred March 18th, 1925. And it occurred over 3 different states, Missouri, Illinois, and Indiana. And the total number of people that perished was 689. And you can see there's some other events that took many, many lives. And most of these locations are in that central United States hotspot that I showed you in the previous graph. One famous Canadian tornado was the tornado of June 22nd, 2007 in Pipestone and Ely, Manitoba. It occurred at 6:25 p.m. in the evening, lasted for about 49 minutes, caused about $39 million in damage. And what's spectacular about this tornado is that it was a true F5, and F5 tornadoes are quite rare in Canada, more common to the south in the United States. If it's an F5 tornado, wind speed is estimated anywhere from 420 to 510 kilometers per hour at the tornado's core. What follows on the next slide is a little video that some storm chasers made of that tornado, and let's watch it for a few minutes, and let's hope that Dave is safe.
Wow! Look at how big it is! Be careful, Dave. Don't watch it too closely.